Hello and welcome. This is video 1 of 5 in our Deep Learning Unit 1 series. In this opening video, we set the stage, what deep learning actually is, the dramatic history of how it rose, fell and rose again, and the 3 fundamental ways machines learn: supervised, unsupervised, and reinforcement learning. We finish with our first interactive quiz. No heavy math yet, just the story and the map. Let's begin. Hello everyone, and a very warm welcome to Unit 1 of our Deep Learning course. I'm really excited about this unit because this is where we build the foundation that everything else stands on. Over this series we'll cover 3 things: linear algebra, which is the language of deep learning; probability, which is how we reason about uncertainty; and numerical computation, which is how all of this actually runs on a computer. We'll be following the classic textbook by Ian Goodfellow, Yoshua Bengio and Aaron Corville. Don't worry if math isn't your strong point, I'll walk you through everything, step by step, with plenty of real-world examples. Let's dive in. So before we start, let me show you the roadmap for this unit. There are 3 parts. Part 1 is linear algebra: scalars, vectors, matrices, tensors, and the famous techniques like eigenvalue decomposition and PCA. Part 2 is probability and information theory. That's where we'll meet random variables, Bayes' rule, and the mathematics or uncertainty. And Part 3 is numerical computation: what actually happens when this math runs on real hardware, include gradient descent, the algorithm that trains every neural network in the world. Here's how I like to think about it: linear algebra gives us the language, probability gives us the logic, and numerical computation gives us the machinery. Keep that picture in your head. Now, whenever I start a unit, I like to be very clear about what you'll actually be able to do by the end of it. By the end of this unit, you'll be able to represent real-world data as vectors, matrices, and tensors. You'll be able to multiply matrices confidently and recognize the standard matrix types. You'll know how to measure vectors using norms. You'll understand eigenvalue decomposition, SVD, and PCA, and not just the formulas, but what they actually mean. On the probability side, you'll be able to reason about uncertainty using distributions and Bayes' rule. And finally, you'll be able to explain exactly how gradient descent trains a model. My suggestion: take a screenshot of this slide. When we finish the unit, come back and check off each item honestly. That's your self-test. Alright, let's begin with our first chapter, the foundations. Before any mathematics, I want us to agree on the basic vocabulary. What exactly is deep learning? Where did it come from? And what are the different ways a machine can learn? This chapter is deliberately light on math. Think of it as the story and the map, and trust me, knowing this story will make everything that follows feel much more natural. We'll finish with our first quiz, so stay sharp. So, what is deep learning? Here's the definition I want you to remember. Deep learning is a subset of artificial intelligence that learns from large datasets using neural networks with many layers, and the keyword there is automatically. It finds the patterns by itself. Let me make that concrete. In the old days, if you wanted to build a spam filter, an engineer would sit down and hand design the features like, count how many times the word free appears in capital letters. That's manual feature extraction, and it's slow and painful. A deep learning spam filter, you just show it thousands of emails, and it discovers those signals on its own, including subtle ones no human would think of. And where does the idea come from? From the brain. The neural network is loosely inspired by biological neurons' brain cells. It's not a copy of the brain, but it borrows the idea. Now, here's a question students always ask me: what's the difference between AI, machine learning, and deep learning? Aren't they all the same thing? No, and the picture is actually very simple. Think of 3 circles, one inside the other. The biggest circle is artificial intelligence, ANY technique that makes machines act intelligently. Even a chess program running on handwritten if then rules is AI. Inside that sits machine learning systems that learn patterns from data, instead of being explicitly programmed. And inside that sits deep learning, machine learning that specifically uses multi-layered neural networks. So here's a quick test for you. A thermostat with handwritten rules. But not machine learning. A spam filter using word frequencies. Machine learning but not deep. ChatGPT, face unlock, self-driving cars. That's deep learning. Every deep learning system is machine learning and every machine learning system is AI, but never the other way around. Okay, so deep learning uses multi-layered networks. But how many layers make a network deep? The answer is surprisingly literal. A shallow neural network has exactly one hidden layer between the input and the output. That's it. It works, but it has limited capacity for complex patterns. A deep neural network stacks several hidden layers, and here's why that matters. Each layer builds on the one before it. In a face recognition network, the first layer might detect simple edges, the next layer combines edges into sharps like eyes and noses, and deeper layers combine those into whole faces. That layer-by-layer composition is the real magic, or depth. But I'll warn you now, deeper is not automatically better. Depth is hungry. It needs data and it needs computing power. And that's exactly the historical story I'm about to tell you. Let me tell you the story of deep learning, because honestly it's a drama in 3 acts, with 2 winters in between. Act 1. In 1943, McCulloch and Pitts proposed the first mathematical model, or neuron. In 1958, Rosenblatt built the perceptron, the first learning algorithm for classification. Huge excitement. Then came 1969. Minsky and Papert proved that the perceptron couldn't solve even simple problems like XOR. Funding collapsed. That was the first AI winter. Act 2. In 1986, backpropagation arrived. Rumelhart, Hinton and Williams showed how to train networks with multiple layers. Interest returned, but computers were too slow and datasets were too small, so the field stayed mostly academic. Act 3 begins around 2012, when everything changed. GPS, big data and better algorithms came together, and deep learning suddenly started winning at vision, speech, and language. That's the revolution we're living in right now. So why 2012? Why not earlier? Let's look at what actually happened. First, remember that in the 2000s, neural networks were actually out of fashion. Support vector machines, decision trees, random forests, these were winning. They were more accurate, easier to train, easier to interpret. Then 3 forces converged. Number 1, computational power. GPS, graphics processing units, were built to render video game pixels in parallel. And it turns out, matrix multiplication for games and matrix multiplication for neural networks is the same math. Deep learning inherited a supercomputer from the gaming industry. Number 2, the internet era produced enormous labeled datasets. And number 3, smarter algorithms made deep training stable. The moment it all clicked, 2012, AlexNet, trained on just 2 consumer gaming GPUs, cut the imagined error rate nearly in half overnight. After that, the entire industry switched. Remember this trio? Compute, data, algorithms. Now let's zoom into machine learning itself, because deep learning inherits all of its basic ideas. Machine learning is the branch of AI where computers learn from data and improve from experience without being explicitly programmed for every task. Here's the way I like to explain it. Traditional programming works like this: you write the rules, you give it data, and it produces answers. Machine learning flips that around: you give it the data and the answers, and it figures out the rules. Think about Netflix. Nobody at Netflix wrote a rule saying people who like sci-fi also like thrillers. The model learned your taste from millions of watch histories, and it keeps improving with every episode you finish, or abandon halfway. That inversion, data plus answers, gives rules. That is machine learning in one sentence. Every machine learning algorithm you will ever meet belongs to one or a few families, and the families are defined by one question: what kind of feedback does the learner get? Family 1, supervised learning. The data comes with labels, every input has the correct answer attached. It's learning with a teacher. Family 2, unsupervised learning. No labels at all. The algorithm has to discover hidden patterns and clusters by itself. Learning without a teacher. Family 3, reinforcement learning. No labels, but rewards and penalties. The agent tries actions and learns from consequences, like training a puppy with treats. And there's a practical hybrid called semi-supervised learning, a small labeled set combined with a large unlabeled one. Why does that matter? Because labels are expensive. Imagine paying radiologists to label 1 million X-rays. You label 10,000 and cleverly use the rest unlabeled. With a teacher, without a teacher, from consequences. Hold on to those three phrases. Let's take the first family, supervised learning, and really understand it. Supervised learning means training on a labeled dataset. Every example contains both the input and the correct output. The classic example, cats versus dogs. You feed the algorithm thousands of images, each one labeled cat or dog. The machine learns what distinguishes them. Then, and this is the important part, you show it a brand new image it has never seen, and it correctly says, that's a dog. That's image classification in action. A real example you interact with daily. Your bank's fraud detection. Millions of past transactions, each labeled fraud or legitimate, taught the model the mapping. Now it scores every swipe of your card in milliseconds. Supervised learning splits into two branches, classification and regression, and telling them apart is our next job. Let me walk you through the supervised learning pipeline on this slide, left to right. We start with labeled data, input 1 with output 1, input 2 with output 2, and so on. That flows into the learning algorithm, whose job is to find the mapping from X to Y. The result is a trained model, the captured knowledge. And finally, we give that model any W input it has never seen, and it produces a prediction. Now here's the sentence I really want you to remember: the moment of truth is generalization. The model must be right on data it never saw during training. Think of two students preparing for an exam. One memorizes all the solved problems word for word and fails the exam when the numbers change. The other learns the method and passes. Memorizing the training set is not learning, generalizing is. So branch 1, or supervised learning, classification. Classification predicts categories, discrete classes. Is this email spam or not spam? Is this patient high risk or low risk? The answer is always one, or a fixed set of labels. On the right of the slide you can see the classic algorithms: logistic regression, support vector machines, random forests, decision trees, k-nearest neighbors, naive Bayes. And here I have to warn you about the most famous trap in machine learning vocabulary. Look at the first algorithm, logistic regression. Despite its name, it is a classifier. Examiners love this trick, so burn it into memory now. Real classifiers you use today: Gmail's spam filter and face unlock on your phone. Your face or not your face. Categories. Branch 2, regression. And the contrast with classification could not be simpler. Regression predicts continuous numbers, not categories, numbers. What will this house sell for? How many units will we sell next month? What's tomorrow's temperature? When Uber tells you your driver is 7 minutes away, that's regression. When Zillow estimates your home's price, regression again. Here's your litmus test, and it works every time. Ask, is the output a category or a number? Predicting a student's exam score, that's a number, so regression. Predicting PASS or fail categories, so classification. One more thing, notice decision trees and random forests appear in BOTH lists. The same algorithm family can do either job depending on the target. The task defines the type, not the algorithm. Now for the second family, unsupervised learning, and this one starts with something missing. In unsupervised learning there are no labels, no correct answers attached to the data. The algorithm must discover hidden patterns, similarities, and clusters entirely on its own. You might wonder, what can you possibly do without answers? Actually, quite a lot. Here's a beautiful example: a supermarket takes its loyalty card data and runs clustering on it. Outcome: customer segments nobody defined in advance, young family shoppers, late night snackers, weekend bulk buyers. The business can now target offers to each group and spot unusual outliers too. This is used for data exploration, visualization, and dimensionality reduction. And keep that last phrase in mind, because PCA, coming later in this very unit, is an unsupervised technique. Compare this pipeline with the supervised one from a few slides ago and notice what's missing. Unlabeled data goes in just inputs, no outputs at all. The learning algorithm measures similarity between the data points. And outcome clusters, groups of similar points that emerged from the data itself. That missing output column is the entire difference between the two paradigms. Same shape or pipeline, but no teacher anywhere. And here's a thought worth pausing on: if there are no correct answers, how do we even know the clustering is good? Think about that for a second. In practice we check whether the clusters are internally tight, whether they're useful downstream, and whether they make sense to a human. It's a genuinely harder question than in supervised learning, and that's part of what makes this family interesting. Unsupervised learning has two main families, and they answer two different questions. Clustering asks which data points belong together. It groups points by similarity using algorithms like k-means mean shift and db-scan. Association rule learning asks a different question: which items occur together? It finds rules like if a customer buys item A, they'll probably buy item B. The classic algorithms here are a priori and FP growth. There's a legendary story about this, possibly exaggerated, but too good not to tell. A retailer ran basket analysis and discovered that beer and diapers were bought together on Friday evenings. Young fathers sent out for diapers, grabbing a six-pack on the way. True or not, that's association rule learning in one image. Customers who buy bread also buy butter. And now the third family, my personal favorite, reinforcement learning. Reinforcement learning is learning by playing. You try actions, good actions earn rewards, bad actions earn penalties, and through practice you learn the best behavior. Nobody ever tells you the correct action. You only get the score. The most famous example is AlphaGo. It played millions of games of Go against itself, getting better with every game. In 2016 it faced Lee Sedol, the world champion, and during that match it played a move so strange, so unhuman, that commentators thought it was a mistake. Move 37. It turned out to be brilliant, and AlphaGo won the series 4-1. Every interaction becomes new training data. The more it plays, the more experienced it gets. Google's self-driving car project trains the same way. And here's a modern connection: the technique used to align ChatGPT reinforcement learning from human feedback is this exact idea. Reinforcement learning runs on one eternal loop, and it's drawn out for you on this slide. Step 1: the agent looks at its current state, ST, and chooses an action at T. Step 2: the environment executes that action and changes. Step 3: back comes a reward, R, and the new state. And Step 4: the agent updates its strategy, its policy, and the cycle repeats. Let me make it concrete with chess. The state is the board position. The action: move the knight. The reward: +1 if you eventually win, -1 if you lose. And notice something tricky there: the reward is delayed. You made 50 moves, which ones deserve the credit? That puzzle is called the credit assignment problem, and it's what makes reinforcement learning genuinely hard. This loop runs millions of times. That's the whole game: maximize the total reward over time. Before our first quiz, let's pause and ask, where is deep learning in your life right now, today? Computer vision face unlock on your phone, medical X-ray screening, defect detection in factories, speech, Siri, Alexa, captions, language ChatGPT, Google Translate, the autocomplete in your keyboard, self-driving cars detecting lanes and pedestrians, healthcare AlphaFold solving protein folding, and every recommendation you've ever received: Netflix, YouTube, Spotify, Instagram. I'd bet you've used at least 3 of these since breakfast. And here's why this list matters for us: every single one of these systems is built from the mathematics in this unit. Images are tensors. Recommendations use matrix factorization, that's SVD, and every one of them was trained by gradient descent. That's the payoff for the math we're about to do. Alright, quiz time. Let's see if the ideas have landed. Question 1. A model must predict tomorrow's exact temperature in degrees Celsius from historical weather data. Which type or learning problem is this? Option A: unsupervised learning clustering. Option B: supervised learning classification. Option C: supervised learning regression. Or Option D: reinforcement learning. Remember, the litmus test we discussed: is the output a category or a number? Pause the video now and lock in your answer. Ready? The answer is C: supervised learning regression. Let's reason through it together. We're training on past days with recorded temperatures, that's labeled data, so it's supervised. And the target is an exact number: 21.7 degrees, 33.2 degrees, a continuous value, not a category. Number means regression. If you picked B, classification, you're in good company. It's the most common wrong answer, but notice the question would need to ask for categories, like hot, mild, or cold, for classification to be right. No labels at all would make it unsupervised. and rewards from trial and error would make it reinforcement learning. If you got this right, excellent. You've mastered the map or machine learning. On to the mathematics. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.